We're going to look at creating a model of a heatsink with a PCB and some components on top of it that are generating a specific amount of heat. We'll start off just by calling our model heatsink and PCB, and we have this in a folder that has some of our other information in it. So we're going to use for our units, we'll use meters. That'll be used for all length properties within our model. I could change it if we needed to. The key plane tolerance, which is just going to tell you that anytime you have two key planes within this tolerance, they'll be merged together. We're using 1/100th of a millimeter, and this is useful just in case you have two solids that are a little bit off of each other. A key plane, one block for instance, creates 6 key planes, 2 on each axis to make up the object itself. So basically they're defining any unique position in a model. Then we have a solution type which is just steady state because we want to know the maximum temperature. Transient would be if we wanted to know the temperature after a specific amount of time or see how it changes over time. The flow regime will be laminar for this case, and we're going to run it with a temperature of 50 as this is both the initial temperature, and it'll also be used for the temperature at the boundary. So anytime flow is coming in for CFD from the outside, it'll come in at this temperature. You can also go through and change individually what temperatures solids are if you need to, especially for a transient case if you have, say, that your heatsink starts at a certain temperature. The gravity by default is in the -z direction, and we'll just leave it like that, but if at any point you need to come back to this form to change that, you can. It's available through model parameters under the parameter section here. And hit apply on this. Now we'll bring in a step file. And just going to import this step file here. What this will do is visually it'll show the step file. It's not actually going to bring it directly into the model. We then have a conversion routine to bring in individual solids within the step file so that we can give them a material and a name before bringing them in, as well as determining what resolution we want to use to import the solids. So looking at this, we have our heatsink, PCB, and then several components on top of the PCB. So first we'll start off by bringing in the heatsink, and we'll give it a name of heatsink, and give it a material of aluminum. Then for the block resolution, we're just going to use 1%, so that's 1% of the overall side would be your sort of smallest resolution point of this model. You could also give it a specified length, but the advantage of the percentage is that it will sort of change with your model. So if you have something that's very small, the resolution will shrink down with it. For precision, we can just use normal for this. As you see, it already looks basically like we're going to want it to look at the end, and go ahead and convert this. And so what this is going to do now is create block files from this specific solid that can then be brought into ElectroFlo and all put into one solid group. So the solid will be made up of several different blocks, all of the same material, and then they can be moved together, or you can change all of the properties at once through using that solid. Okay, so once that's done, we now see our heatsink here. It's come in nicely. The graphics are a little messed up by the video capture routine, so bear with me on that. From this point, we could either retry to create it. If we didn't like this, we could use a different resolution and retry, discard it to get rid of it altogether, or just accept it, and then that'll actually bring it into the model. So it's not really in your model until you click accept there. So now we come back here and we can see that that's no longer there because we've brought it in. So next we'll bring in the PCB. We select the PCB, give it the name PCB, and we'll give it FR4 as the material. I actually already have FR4 in my library, so it'll just use that. If I didn't, then it would create a new material called FR4, and then I could go through it and give it the properties. For this, since we really just want this to be one block, I'm not really worried about any hold any cutouts on the PCB or anything like that. I'm just going to use percentage of 5, so bump it up a little bit more, and everything else is fine. So this will make the conversion routine a little bit faster. It'll also, as you see now, we just have one single cube or rectangular cube for the model. So we accept that. So now we have our components left. And looking at these, we need to go through and name them. So I'm actually going to rotate them like this and fit the zoom. Now, if we look here, this is a PCB plot that we have. And we can see the naming convention of all of these. So since this is D1, D2, D3, D4, what we'll need to do is select them in the order that we want them to be named. So we'll select, if we go back to the ElectroFlo model, we'll select this, select here, select here, select here, select here, and then here, and we'll give them all the name of just D, and then it'll go through and add 1, 2, 3, 4, 5, 6, all the way to 8. And we'll just give these a material of comp D, so we're going to set that later. For this case, we're not going to actually model the internals of the components. We just really want a very sort of rough estimate of how much temperature gain we're going to get from this model, and if this is even going to be something that can work, because we don't actually know the details of our PCB yet. So I now go through and select all of these. While holding Shift, I select in the order that I want them to be named. And the 5% should be fine, and hit Convert. So this has now brought all of those in, given them the name, given them that material. We accept that. Next we have the last 4 components. We'll give them a Q. And once again, go through and select them in the order that we want them to be named. Okay, so now we have all of our model brought in. We can accept that. You can see now I don't have anything left, so I just click Done, and it'll come back into my actual model here. So the last step of the geometry now, we've brought this in, we just want to clean this up, and in this case it's fairly simple geometry, it doesn't really even need to be cleaned up, but if we look at the edit mesh here, we can see that we have a very, very manageable amount of elements, so there really isn't a need to clean it up, but we're going to anyway, and go into key plane edit here, model verification and adjustment. And what we're going to do here, if I look at the key planes, you can sort of see any key planes made at each block, to make sure that there aren't any that are closer than we need. So we have that tolerance set, so anything closer than 0.01 millimeters will be automatically merged, but really I think for the case of this geometry, that's even too big, so I'm going to make it anything less than 0.2 millimeters we'll get rid of. And allowing a complex solid collapse would just mean if say for this is made up of lots of little blocks, if there was a little block in here that would need to be completely collapsed and sort of discarded, that would allow that to occur. And as we go through the solid key planes, we find that there's 13 key pairs found, and we can go ahead and merge those. Now we could go one by one and look at what's there to merge, and merge either on the left and the right. In this case, I don't really care, so I'm just going to select left and then do yes for all, and that'll get rid of that. So now, if we do look at our mesh, it's now reduced by quite a bit. Still very manageable, and we could modify that if we needed to.